Okay, hopefully I'm recording. All right, so I have to stand back here now. So anyway, yes, there's an impulsive force there. It's coming between the car, right? Because the collision occurs over a very short period of time, and it is a huge force. It's an impulsive force. Got it? So what's going to happen is I'm going to ignore everything else, okay, that's not impulsive. How about the weights of the cars? The weights are pretty large, aren't they? But they're there forever, and they are nowhere close to the size of that impulsive force, right? Because if they were, you'd set your car down on the ground and it would crumple. It doesn't, right? So it's nowhere near the magnitude of that impulsive collision. Make sense? Do you think there might be friction underneath them? Yeah, maybe, right? Because they got the brakes on probably. You know, I don't know, right? Is that impulsive? No, so we're going to ignore that. We're going to ignore the gravity, we're going to ignore the friction, we're going to ignore everything except that one huge force on the front of the automobile. Okay? All right. And it's an approximation, right? It is an approximation because the weights of the cars have something to do with it, but it's so small compared to the other force. It's so big. You get the idea? Okay. So I'm going to draw a free body diagram. Okay? When I draw a free body diagram, I see two objects in there. So I'm going to draw two free body diagrams. Here's A. And I want to draw the force that's on A. And I'm only worried about the impulsive force. Okay? So I'm going to draw it like this. Here's this big impulsive force. I'm going to call it F. Do you know how big it is? I don't either, so I'm going to call it F. Let's draw the free body diagram of B just for kicks. What do you have on it? The same force, equal, is it left? To the right. Newton's, what is it, whatever law, whichever law it was, third law, I guess, equal and opposite. So if I push you, you push me. If I pull you, you pull me, right? So there you go. Same force, one's left, one's right. I don't know what that force is, and I don't want to deal with it. Did we do any problems in this class where if you choose the correct system, you don't have to worry about a force? Yeah, remember the guy on the bicycle? I think it was in the last chapter or something, right? What if you take A and B together as the system? What would happen? Yeah, the F force is now inside. Right? And I don't have to worry about it. That's what I'm going to do. I'm going to take A and B together as a system. And it's the split nanosecond before they hit to the split nanosecond after they hit. That's what I'm worried about. Just that really short period of time when, bam, that impulsive force is active. Okay, that's what I'm talking about. That moment right there. Okay? Now what I'm going to do is I'm going to go in and I'm going to say, all right, I remember that I had this equation, and yeah, I realize I didn't say it real well, but it was like this. It was impulse. Impulse equals change in momentum. The delta means change, right? Impulse equals change in momentum. On the previous slide, I told you what impulse was. You remember? Probably not. It's the integral of the force. The time integral of force. That's what impulse is, okay? Look at that free body diagram AB. You see any forces on it? Okay, then the force is zero. What's the integral of zero? Integral of zero. Zero. Right? If you're integrating, you got nothing. I got no impulse. I have no impulse. Right? No forces. Isn't that weird? What does that tell you about the change in momentum? MV final minus MV initial. That's change, just like it was in work, right? I told you change is always final minus initial. Momentum is mass times velocity. Final minus initial, that's change. What does it tell you about the change in the momentum? It's equal to zero. Does it change? Does the momentum change? No. Do you like that idea? No, but that's what Newton said, and he hasn't been wrong yet, until Einstein came along, right? Okay. But I mean, that was a long time. And for slow speeds, he's right. It's only at the high speeds that he's wrong. right? Newton says, hey, that's the way it works. That's the way it works. You may not like it, but that's the way God made it, and that's the way we discovered it to be. Okay? So there you go. So what am I going to do? Well, what I'm going to do is I'm going to say the final momentum is equal to the initial momentum. Okay? So let's go get the momentum. What's the final momentum? Well, let's see. These guys are moving, I don't know, to the right or to the left. Any ideas? What do you think? You think they're going to go to the right after they collide or to the left? Yeah, you can sit there and spend 5 minutes, but I'm going to solve for it. So does it matter? Okay, what do you think I'm going to do? I'm going to say it's going to go to the right because I'm going to get a plus or a minus sign saying you're right or you're wrong. Okay? And then I don't want to go looking back to see what I did this time. I'm going to try and do the same thing every time. Okay, so I'm going to say, well, I don't know. But I think they're going like this. I think they have a final velocity. I'm going to say VF. And I think they're going to go to the right. Okay? What's the final momentum? Okay. How fast is A moving? VF. So mass of A times V final. That's his momentum. Is it a plus momentum or a minus momentum? Plus? Okay, so we're going to call this direction over here plus. All right, so that's a plus momentum. How about body B? It says they're entangled. Does he have a momentum? Yes, he's got a mass, he's got a speed, right? How much? Oh, he's got a mass B times the final velocity. Is he a positive or a negative? Now, wait a minute. He was headed to the left. Yeah, once they're together, I think they bounced back. So that should be a positive also. Has nothing to do with what they were doing beginning, right? This is the final. What are they doing at the end? And that equals initial, right? Let's go get their momentums before they collide. Okay? Does A have some momentum before they collide? How much? Mass times speed, right? So here we go, mass A. What's the initial speed? 3 feet per second? Positive or negative? Does B have some momentum? How much? Yeah, it's negative. Mass B times how fast is he going? 6? Positive or negative? You sure? Absolutely. How many unknowns? 2. 1 unknown. How many equations? 1. Can you solve that? Yes. You're going to get either a positive or a negative. I don't remember. You're going to get a positive or a negative. If you get a positive number, what does it say? Yeah, A, they smack into each other and A kind of pushes them back. What if you get a negative number? Went the other way. That's all it means. Is that easy? Easy peasy, right? Yes. Just like the energy. When there are impact problems like this, they really are pretty simple. Okay, what did we do? What we did was we said we're going to ignore all forces that are not impulsive, and then what we're going to do is we're going to look for systems, put multiple masses together so that all of those impulsive guys disappear. That's what we're going to look for. Okay? A dead giveaway is an impact on an exam. A dead giveaway, you see an impact. Why? Because it's an impulsive force. Impulsive forces, you're going to ignore everything else. Okay? So that's how you'll recognize it. Okay? So on the final exam, you're going to read the thing and you're going to say, ha-ha, that's an impulsive force. What are you going to do with this technique, right? If it's not a collision, no impulsive forces, then what are you going to do? You're going to say, maybe it's an energy. And you're going to boop, 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 3 questions, and it is or it isn't. If it is, it's easy. Should be. Right? If it's not, what are you going to do? You're going to throw something at me and cuss at me, right? But you're going to go back to the old stuff. And how will you know to draw a free body or not? You remember that? Okay? So all the old stuff could be there. Yeah.
Let's bring the example where they have the plate.
Yeah.
If we didn't ignore the mass of the plate, they would use this.
Right. What I would do is you use what he was talking about, you have this plate with a mass. Here's what you do. This is a classic problem. It shows up on a lot of exams, by the way. So what happens is you drop the ball, and it falls down, hits the plate. Okay, it has a mass, it's got a mass. You got a coefficient of restitution because you know they're rubber balls or whatever, right? So what will happen is you use energy from here down to just before it hits, and you can use energy for that. Okay? Now you know how fast the ball is moving when it gets down here. Now it's an impact, and I'm going to do some impacts, so balls hitting balls and stuff like that, so you'll know how to do that. So then you do an impact here. And that tells you how fast the plate's moving. And once you know how fast the plate's moving, then you use energy from then on back. Okay? So you break it down. Energy till it gets here, impact, and then energy there. And the ball may bounce back up, who knows, right? Make sense? A little bit? It's kind of a classic sort of problem. Okay, shall we do another one? How about this one? I think this is actually a homework problem. So you'll be able to see if I get it right or not. 200-gram projectile is fired with a velocity of 900 towards the center of the 15-kilogram wooden block, which rests on, the hardest part about this is reading this thing, rests on a rough surface, so there is friction. Let's see, if the projectile penetrates and emerges from the block with a velocity da-da-da, determine the velocity blah-blah-blah. How long does the block slide on a rough surface after the projectile emerges before it comes to rest again? Coefficient of kinetic friction between the surface and the block is 0.2. Okay, let's say this is on the final exam. What do you do first? You want to rule out if it's an impulsive momentum. Right? Rule that out. When you rule it out, what do you look for to rule it out? You say, there are no impulsive forces acting on this thing. No, are you sure? Think about what happens when that bullet goes in there. What's the force going to be? Small or big? It's huge, man. That bolt's going to go all the way through, right? Isn't that a huge force? I mean, you don't believe it? Have your buddy shoot you. No, don't do that. Right? I mean, it damages you. Why? Because it's hitting you hard. Hitting you hard. Right? There's a little rubber bullet, right? Your little baby brother or something, you know, shoots you with the little darts. Does it hurt? No, because it's not a very large force. You get the idea? So can you spot the fact that this is an impulsive force? I hope so, because I don't know how else to tell you to do it. You look at that and you go, oh, heck yeah. Maybe what you do is you say, would I want to get hit with that? No? Okay, then it's probably impulsive. Okay? So is this an impulsive momentum problem? Yes, it is. Why? Because there's an impulsive force on it. Okay? How do you do those? Well, I'm going to look for a system. I'm only going to include, during the collision, I'm only going to include impulsive forces. Right? So let's think about the forces and see which ones are impulsive. I've got friction. Is that impulsive? No. It's mass times gravity times mu, right? That's a real small number. Even if it's a heavy block, it's real small. Think about the bullet force, right? Compared to the man, that's not impulsive. No. How about weight? Impulsive? No. Normal force, impulsive? No. Bullet force between the bullet and the block? Yes. Okay, that's the only one, right? So what I'm going to do is I want it to disappear. So how do I choose masses to put in a free body so that that one impulsive force disappears? What do? Combine them. You combine them. Right? So I'm going to combine them. I'm going to take the bullet and block together as a system. Okay. How much impulsive forces do I have when I take them together? None. I have 0. I can hear that bowl feeder buzzing up here, so it's going to be interesting when I post this. I wonder if the recorder is going to pick up that buzz. There'll probably be this bzzz in the background. Okay, so there's no impulsive forces. Okay, what did Newton say about impulse equals what? Change in momentum, right? So this is equal to change. I don't know why delta. Okay, change in momentum. Momentum is mv. Got it? So what does that tell me about the change in momentum? It doesn't change. That's what it tells me. It does not change. Okay, so here we go. What is the momentum after the collision? Is the bullet moving? Okay, so let's get the, this will be final. So the mass of the bullet, BU, how about that? Mass of the boo times what? Yeah, what is the final velocity? 300, okay. Is it positive or negative? Positive? Because we want this guy over here to be the plus direction, right? How about the block? Does it have some motion? Does it have some momentum? Probably. Probably. How much? Well, it's going to be the mass of the block, BK, times what? The velocity. Do you know what it is? How about we call it V? Is that good? That's the final velocity of the block. Should I put a plus or a minus here? Well, it depends on V, right? I don't know which way it's going. Well, we do, right? I don't know which way it's going. I'm going to assume it goes to the right. So I'm going to put it in as a plus. Now, when I solve for it, I'm going to get a plus or a minus on the V, right? A positive number on V. What does that tell me? I'm correct. A negative, what does it tell me? I blew it again. We know it's going to end up being a positive because, right, you don't shoot something that comes at you. Well, maybe a bear does, right? But a block, no. Okay, equals. What's the initial momentum? Okay, does the bullet have some? Okay, that's going to be mass of the boo times what? 900. Positive, very good. Does the block have any? Why not? Zero velocity. Can you find the final velocity of the block? Bingo. Somebody already did the math. So you can find that speed, correct? And it ends up being a positive number. Okay. What was it that they wanted me to do? He says, how long does the block slide on the rough surface after the projectile emerges? So, okay, I know how fast it's going. I need to know how long will it take until it stops. Is that an energy? Let's find out. Let's find out. Is it a time spanner? Yes. Can you find the energies, the works of all of the forces on there? Yes. There's friction, there's gravity, and there's normal. That's it. Those are easy. Right? Boom. Number 3, do you want to know what time it takes? Shoot, it's not an energy problem. How about I change this to make it an energy problem? Is that okay? Because we want practice on that. I'll do it both ways. Okay? How would I change this so it becomes an energy problem for the final exam? That way I can snag you with 2 of them at once. How far does the block slide before it comes to rest? I don't care how long. I want to know how far. Is that an energy problem? Yes, because it's a time spanner. I can find the works, and I don't care how long it takes. Okay, so we'll change it and make it an energy just for practice. Okay, how far does the block slide on the rough surface after it emerges before coming to rest? Boom, one change of one word, and all of a sudden I got you doing something wrong. Watch out. I'm like that. You just thought I was a nice guy. Or maybe you didn't. I don't want to know. I don't want to know. Okay. So anyway, how am I going to do that second problem? It's now energy, right? What's it? You remember the energy equation I used? Energy in minus energy out equals da 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 da. Okay. Do you have any energy going in? No? Do you have any energy coming out? Friction. Okay. How much is the energy, or the work, I should call it work, how much is the work of friction? It's the force times the distance, right? The force is going to be mu times normal. Do you know how far? Now let's call it D. Is it a positive energy or negative energy? Positive work or negative work? Negative. 2 reasons you know it's negative. The block is moving this way. The block is moving that way. And the friction is that way. It's opposite. Okay, so it's a negative. The other way is friction speeded up or slowed down? slows it down, it'll be a negative work. Negative work slows things down, positive work speeds them up. Okay, minus mu in any other energies coming in or going out, work or anything? You got any heat in there, anything like that? No? Okay. Equals what? Final energy. Does the block have any kinetic at the end? It does? At the end? Kinetic? He stopped, right? Okay, so no kinetic at the end. Does he have any gravity potential? Well, it depends on where you choose the zero gravity potential. How about we choose right there to be the zero gravity? Is that good? Okay, does it have any final gravity energy? No? Okay. Anything else at the end? Is there a spring somewhere? Is there anything I'm overlooking? No. Minus. Let's do the initials. Does it have any initial kinetic energy? After the bullet comes out, does it have any? Okay. 1/2 mass of the block times speed squared. Does it have any gravity? No? Anything else? No? Okay. How many unknowns? 1. How many equations? 1. Right? Boom. You can find the distance. Piece of cake, right? Let's find the time. Okay, if I go back and do the original problem, it's not an energy. So I'm not going to try to use energy. Okay? All right, how many degree of freedom is it? I want to know if I need a free body. That's what I want. How many degree of freedom is it? 1 degree of freedom? How many motions are told to me? How many accelerations? It's a time spanner, right? That should back up. It's a time spanner. That means I'm going to get the A and integrate. Right? That's what it means. I'm going to get the A and integrate. All right. 1 degree of freedom. Did you give me an A? Darn it. What does that mean? I need a free body diagram. So here we go. Now you may be doing it in your head saying, I don't need one. Well, that's fine. But unless you do it in your head, you need a free body diagram. Here we go. You got to, oh, by the way, how are you going to find the normal? Yeah, you've got some forces vertical, right? Okay, so you have mg down, you have normal up, and you have your friction here. Is it sliding? Yeah, so I do know the friction force, right? How much is the friction force? Mu Kn. Okay, any other forces? Don't think so. Okay, what am I going to do? I'm going to sum forces in the vertical, I'm going to sum forces in the horizontal. Okay, so with sum forces vertical, minus mg plus n equals 0. Yeah, you knew that. Okay, sum forces horizontally, minus mu Kn. That's it. That equals mass times acceleration in the horizontal. I think it's accelerating to the right, because that's what I always do. Is it? It's not. What do I get for A? Solve the A real quick, like in your head. It's a negative number. What does it tell me? Dummy. It doesn't go to the right like you thought. Why am I saying it looks like it goes to the right? There's a plus sign there.
It's slowing down.
Right, so I should have known better, right? But what do? I say, I don't care. Shove it in there, I'm going to solve for it anyway. I'm expecting to get a negative, and I do. Right? I'm expecting it to tell me, you big idiot, you're wrong. Sure, yeah. But what I do is, you know, you can do it any way you want, but what I find is when I have to start shoving negative numbers in, I make mistakes. I'll forget the negative, and I'll lose track of them. So I want everything to be positive if I can, right? Plug it in as a positive. It makes more sense that way. If you disagree, put it in as a negative number. I don't care. And then what are you going to get? If you had your negative right here, what would you get? A positive number, meaning yes, you're right. I would have exactly the same number, but it would be a negative saying, I'm wrong. Hey, what do? I always think it goes to the right. I'm wrong. It goes left. You okay? All right. Can you find the A? Is it constant? How do you integrate and find positions, velocities, and that sort of thing when you have a constant acceleration? Kinematic from chapter 12. Right? You don't have to use those, but you'd have to integrate it. Might as well use chapter 12. Okay. What am I looking for? Distance? Oh, time, you're right. I'm looking for time, okay. So I'll say, all right, I remember this one, V final equals V initial plus AT, and that's it. Okay? So here I'm going to plug in, what's the initial velocity? Nope. It's V. It's the one I solved for, right? So this is V that came out of the block, right? What's the final velocity? 0. He stops. Plus, what am I going to put in here for the A? Minus mu K N over M times T. How many unknowns in that equation? 1. Can you solve it? Okay. Was it really hard? Well, it took a little longer because I had to draw the free body and all that. Now, maybe you do it in your head and say, well, hey, anybody knows that the acceleration is equal to, okay, well, bless you, but the free body will tell you. So if you say, well, I didn't know that. Well, okay, you draw the free body, right? Follow the procedure I told you. Right, and why? Well, because while the bullet's going through there, man, you got a heck of a force on there. That bullet is pushing, it's impulsive. I have no idea what it is. Don't draw a free body diagram. Don't do that. Because you don't know what's going on, right? Remember the guy on the bicycle, the problem on the bicycle? Why did you put the guy in there with the bicycle? Why did you do it? Maybe you didn't, but you should have. Well, because he had his butt on the seat, he had his hands on the handlebars, he had his feet on the pedals. Do you know how hard he's pushing on those? Do you know if he's pulling back or leaning up? You don't know anything about what's going on inside, right? So how did you solve the problem? You said, I want to choose a system so all that stuff disappears. Right? And that's exactly what you do to these problems. You got that massive bullet going through there, and man, it's ugly, oh, horrible. Then choose a system so that you don't have to worry about it. You get it? Okay. Shall we move on?
Also, if you want to add some volume to the graphic, maybe the volume should be the block is
I have one coming up. How's it? Okay. Watch the next one. How about that one? Does this work for you? Because what's going to happen here? The bullet goes in, right? And then what does the block do? Slides up. So now we got some change in elevation. Okay. All right. 10 kilogram block is held, blah, 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 da, da, da. On the smooth inclined plane by the stop block at A. If the 10 gram bullet, watch the units on this stuff, especially with bullets, because they're weird units. 10 gram bullet traveling 300 meters per second becomes embedded in the 10 kilogram block. Determine the distance the block will slide up along the plane before momentarily stopping. Ouch. Okay. Final exam time. What do you do first? You either accept or eliminate the impulse stuff. Right? So, what do you look for to see that this is an impulse problem? What do you look for? Impulsive forces. You have it. Where are they? Be careful. The bullet in the block. Where else? Block in the plane. Why is that one impulsive? That's right. When this thing comes in like this, right, you've got a huge, huge force that's horizontal. And what's going to happen here? Is it going to generate a relatively large force normal to hold it on the plane? Is that what's going to happen? So you're going to have two impulsive forces. One is that bullet, the other one's the block, or the normal. What about mg? Is mg impulsive? No. What about if there was friction? Would friction be impulsive? Careful. What would friction be? Un? Roughly Un? Is N impulsive? Is friction impulsive? Yes. When you shoot pool, right? If you shoot pool the way they teach impacts, you'll lose. Right? Because the way they shoot, the way they teach impacts in here is there's no friction between the balls. You've heard of English? That's what I call it. Spinning the ball. Right? That's how you win pull out. You spin it. Well, what happens? Well, what happens is one ball is spinning, right? Comes in, hits the other one, and while it hits, that friction force has now got a normal force, which is impulsive. So what happens to the friction? It becomes impulsive. So part of that spin on the cue ball gets imparted to the ball that you're hitting. So you can make that other ball spin. So you drag the rail, right? That's how you do it. If you can't drag the rail, you need to go drink some beer and hang out in the pool. That's what you need to do. Okay. All right. So what's going to happen is going to be impulsive. After the bullet hits, I mean, it's boom, like that. Bullet's embedded. Then what am I going to do? Tell you what, let's do it later, and then I'll let you think about it a little longer. Okay, let's do the impulsive stuff. All right, blah, blah, blah. Kilogram bullet embedded, determine the distance the block will slide up. Here's what I'm going to do. I'm going to find the velocity of the block after the collision. Okay, I'm going to find the velocity of the block right after the collision. Okay, now, think about the impulsive forces. Normal and bullet. I'm going to choose the bullet and the block together. So I'm going to draw it like this. And here's this bullet, partially embedded. Do I need to draw the force between the bullet and the block? No. Is there another impulsive force? Where is it? Right here. It's in that direction right there. That's the normal. Do I need to draw mg? No. Why not? It's not impulsive. Okay? There you go. There's the forces. Okay? Tell you what, can I sum forces in the normal direction right here? Good. And what would it do? Not much. Right? What if I sum forces this way? What should I get? Do I have any forces do I have any impulsive forces in that direction right there? No. Right? The normal is perpendicular to that. What about this big bullet and all that mess? Inside, inside, baby. Don't need it. Right? So what do you think I'm going to do? I'm going to apply impulse in this direction only. That's what I'm going to do. Because the only thing I get here is I get the formula for n. I don't want it. I don't care. If you want it, go ahead and get it. I don't want it. I just want to do it here. So I'm going to apply impulse in this direction right here. Okay? All right, so here we go. Do what? Yeah, it's the moment, right before the bullet hits the moment, right after it finishes embedding itself, all that impulsive force is on it. And the impulsive forces will occur over a very short period of time. Will the block move? Well, yeah. How far? Not much. Why not? Because it takes time, right? It takes time for it to get up and start moving. So did it go very far? No. I'm going to choose to ignore that. Am I exactly right? No. No. But that's what physicists get upset about. Because we say, hey, this is engineering. You got to get close enough. Right? And that's what it's all about. You got to get close enough. Let the physicists worry about the center of the universe. I want to go make some money. And play some pool. Okay, anyway. So I'm going to apply momentum in this direction. Okay, do you have any impulse in that direction right there? No? Okay, so impulse, 0. You notice there's a key to this. If you can't find the impulse, you can't use impulse momentum. Okay, so impulse is 0. That equals what? Change in momentum in what direction? Along the incline, right? That's what I'm doing it in. So I want the change in momentum along the incline. So this would be change in momentum, mv. Should we call this we'll call it the p direction for the plane. Is that good? Okay, so I want the mv in the plane direction. Is that good? Okay, and we'll say up is positive there. That's a positive. Okay, let's plug in. After the collision, do you have any momentum in the plane direction? Sure do. The block is moving, or it might be. right? So how much momentum do I have for that? Oh, I have mass of the block, velocity of the block. Do you know how much? How about we just call it V? Is that good? Do you know if it goes up or down the incline? I don't care. Everything goes up. That way it goes in as a plus V. How about the bullet? Is the bullet moving along? Really? Isn't it embedded in the block? If the block's going, the bullet's going. It's real small, I grant you, because it's only 10 grams. But if you punch that into mastering, I bet you anything, it takes off. So yeah, there will be a mass of the bullet with the same velocity. That equals the initial. Okay, the initial. All right, so initially, this guy's moving like this. I'm going to draw in the speed. Boom. This is the initial velocity. Okay, so does the block have any initial velocity in the plane direction?
No.
Okay, so the block has no initial momentum. Does the bullet have some initial momentum in the plane direction? Yes, it does. How much? It's mass of the bullet times what speed? It's not 300. Yeah, it's 300 times the sine. It's either sine or cosine. I got to think about it now. This angle here is 30 degrees. So let me change colors. So what I'm looking for is, boom, I thought I changed colors. There we go. I'm looking for a triangle like this. Now I'm looking for this direction right there. See that? So is it cosine of 30 or sine of 30? Cosine of 30. Anybody else have, oh, and is it a positive momentum or is it a negative? Positive? Okay, how many unknowns? One. Can you solve it? Yes. It's real easy to solve, right? That gives me the velocity of the block and bullet, after the collision, the moment after the collision. Now, let's do the second step. What do they want me to do for the second step? Find the distance it goes before it stops, okay? It's not an impulse, right? This second part's not an impulse. You agree? Okay. Next thing to check is it an energy? Because those are easy. Okay? Is it this is the second part of the question, a time span? Yes. Do you want to know the time? Can you find the work by all of the forces? Yes. Because it's gravity, it's normal, it's there's no friction, right? So yeah, I can find that. Okay? So this looks to me like a perfect energy. So let's do it. Okay? Do you have any work? No work. What's that equal to? Final minus initial energy. Okay, so let's get the final energy. Do you have any final kinetic energy? No? Okay. Do you have any final gravity potential? Yes, okay. So for example, here's where it starts and it's going to go up. It's going to go up to here. Whoops, I can't draw it. It's going to go up to there, right? So let's call this the zero gravity. Is that good? So what I'm looking for is I'm looking for the vertical height right there. MGH, vertical height. Okay? What do you want to call this distance from this corner to this corner? Whoa. D? We call that D. That's the distance up the incline. Is that good? All right. What's the final gravity energy? mg. What's the h? D sine 30. Right? D sine 30. Is it a positive energy or a negative energy? How do you know it's positive? He's above the zero. That's why. He's above the zero. He's positive. Anybody else got energy at the end? Be careful. Think about it. This is where you're going to mess up. Not necessarily on this one, but this is where you mess up. You'll forget something. There is none. Minus. Okay, how much initial energy do you have? Do you have any initial kinetic? How much is it? Which M? Yeah, so this one here, yeah, it's the mass of the block plus mass of the bullet. And it'll, you know, I understand it's only 10 grams. It's probably very, very small, but I bet you anything Mastering's watching for that. Okay, so this is going to be mass of the block, because they're together, right? Plus the mass of the bullet. That's what goes in there. 1/2 m v squared, yeah, initial, okay, v squared. Do you have any initial gravity? No? Okay. Plus no gravity. Do you have any springs or anything like that that you're forgetting? No? Okay. Anything else? How many unknowns there? D. Boom. Real easy. Impulse and energy are really pretty simple. Okay? The hard part about the energy is you've got to read it carefully, because they're in the units here, like grams and stuff like that. Watch out for the units and watch out for those, because the wording is, they'll be weird. Okay? They'll be weird. Okay. I think I have one more. You want to do one more? Yeah, you have a question? Do what? Okay, that is the initial momentum. No, that's the initial momentum. So here we go. You see this guy? Let me put it in a different color. I'll put him in blue. Here's the initial velocity right here. How much of that is in this direction right there? So that's the angle 30, and what you're looking for is that side of the triangle. See that? Okay. That's the cosine. Does that answer your question? Okay. I think this is the last one. Two smooth disks, A and B, each have a mass of blah, blah, blah. This is the only one I've got that has a coefficient of restitution, so we'll one your size. No, that's not bad. It really isn't that bad. Okay. Two smooth disks, A and B, each have a mass, blah, 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 and they collide, they move this. After the collision, B moves along the line 30 degrees, kind of, okay, whatever. Now, how are you going to do this? Final exam problem. So how are you going to do it? Where do you start? You're going to say, maybe it's an impulse momentum. What do you have to ask yourself to see if it is? Are there any impulsive forces? Are there? Yes. Because they bang together, right? So there's impulsive forces. And that's why you're not going to use energy. Right? They're going to bang together. Right? So yes, there's an impulsive force. Okay? What do you do about that? You think about what the impulsive forces are. What are the impulsive forces? The collision forces, when they boom, they bump into each other. Is the weight? Is the anything else? No. Even if, this is on a table, right? So they're like, what's that, air hockey. So like air hockey, right? But even if they were in space flying, you would ignore the gravity. You would ignore it because you're going to solve the problem just the moment before they collide and just the moment after. And the gravity is not impulsive. It will make a difference. That's why the physicists get upset. We say it's so small, it's going to be like 10 to the minus 6. Who cares about that? You can't even measure it. Right? We're going to ignore everything that's not impulsive. So even if this shows up on an final exam and there are balls flying in the air, you're going to do it exactly the same way. And you're going to say, yeah, but they're going to fall away. No, right? Yeah, it's going to take time for them to fall away. But the moment that they smack, gravity's not doing anything. Hardly. Okay, so there is an impulsive force. What are you going to do about that? You're going to take the two bodies together. That's what you're going to do about it. Okay? Now, these are two guys colliding. Where's the normal direction? It's right here. Here's the normal. Where's the plane direction? Okay? So what are you going to do? I'm going to take the two masses together, and I'm going to try to apply impulse and momentum. Okay? So here we go. Is there any impulsive forces if you take the two together? No? Okay, so impulse equals 0. Okay, I won't argue. I'm going to take you somewhere, but I'm not going to argue with you yet. 0 impulse in the x, we'll do x, or normal, equals change in momentum in the x. That's fine. Okay, what does that mean? It means initial equals final. Okay, so let's do the initial and final. Okay, initially, what's the momentum of A? Let's see, they are both half a kilogram, so 0.5 times what? I'm doing x. Times 6, and it's negative momentum, right? What about B? I've got a mass of 0.5. I've got a velocity of how much in the x?
4.
Yeah, 3/5 of 4. Positive or negative? How about the end? What do we know about the end? Equals. Okay, let's go back and read what the heck they were saying. They say that after the collision, B travels along a line 30 degrees counterclockwise from the Y. Okay, I'm going to draw that. 'Cause, man, I don't know what they're talking about. They're saying the guy takes off like that, and this angle here is 30 degrees. Isn't that what they're saying? Okay, so after the collision, what is A doing? In the X, I'm only doing X right now. What's A doing in the X direction? Okay, he's going to be mass 0.5. In the X, he's either going to go right or left. Which way do you think he's doing? I don't care. I'm going to put him into the right, and it's a positive, and I'm going to solve for it, and I get a plus or a minus. So I'm going to say he's a positive VAX. What about B? Yeah, I got a 0.5. What's the X component of that? Well, I'm going to say he's the speed times what? Sine or cosine? Sine of 30? That's the X component of velocity after the collision. Is that a plus or a minus? That would be a minus. How many unknowns? How many? 2. How many equations? 1. I need another equation. Okay, where am I going to get it? Oh, coefficient of restitution. Coefficient of restitution equals, it's a negative, don't forget that negative, and it's velocity of departure divided by the velocity of approach. What that means is it's B minus A over A minus B. Let's see, is that right?
Yes.
Yeah, okay. So it'll be the velocity of departure, okay? That'd be the velocity of B in the X direction minus the velocity of A in the X direction. That's how fast they're separating. You agree? Well, that's what it is, whether you agree or not. And then divided by the velocity of approach. Here's what I remember. VA, you reverse them. VAX initial minus VBX initial. What I'm confused about is there or is there not? No? No negative? Okay. Man, I knew I should have read the book before I came to class. Okay. This is the what I remember. It's B minus A over A minus B. Or it's A minus B over, it's you flip it. Right? It's departure, it's final. Right? Here's what I remember. It's final over initial. And you take one minus the other, and then you reverse it. Boom, boom. What I don't remember is whether or not there was a negative, and I think your author does it backwards for me. That's what really. But anyway, it's the same thing. Okay. So I think what your author does is it says it's minus B minus A, B minus A. I think that's what your author does. But I believe this is correct. Anybody got a book? I'll look it up real quick. I believe that's right. If I'm wrong, I'll send an email to everybody. So far, so good? How many, can you plug numbers in here? Can you plug numbers in? Right? Okay, how many unknowns now? There are 2 more, are there? Yeah, but I already counted it. VAX, so I can solve them. What are the 3? Okay, okay, you got me confused. VBX at the end. VBX at the end is equal to the speed times the sine of 30. VA in the X at the end is equal to VAX. Right? VAX initially minus 6. VBX initially 3/5 times 4. How many unknowns? Let's see. VAX and just the 2. Just the 2. So I can solve it. I thought we had E. Well, okay, then 3. So I need another. Even if I gave you E, there's something you don't know about A. What do you not know about A? You don't know where it goes. You know the X. What about the Y? Correct. Right? I don't know the Y. What am I going to do about that? I need another one because I don't know the E. But I need another one. Period. I need another one. Where am I going to get them? I need to find something that has no impulsive forces. What if you separate the balls out? One at a time. Separate out the A. Okay, just take A all by himself. What are the impulsive forces on him? There's only one, right? And doesn't he go like this? Some big impulsive force right there. Right? Isn't that true? What about in this direction? What's going on in that direction? None? Hey, I'm going to use impulsive momentum in the vertical direction on body A, all by himself. No, because there's no impulsive forces in the Y. That's why. Right? Because there's no impulsive forces. That's the key. You've got to find something that has no impulsive forces. And I found it. Exactly. In the Y direction, A's initial momentum is equal to A's final momentum. Right? In the Y. In the Y. Okay, here we go. What is the initial Y momentum of A? 0. What is the final Y? It's equal to the mass of A times the velocity of A in the Y direction after final. Can you solve that for the final velocity of A? 0. Now, for those of you that shoot pool, you'll say that is baloney. I know darn well it doesn't do that. That ball does not bounce straight back. You're right. And what's the difference between the bowl or the pool and this? Yeah, on the pool balls you have friction. Here, do you have any friction? No. When this ball comes in and smacks, there's nothing that causes it to go up and down. Now, in pool, yeah, it will come in like this and do a glancing blow off of it, right? And that friction will be impulsive. And so you're going to get this impulsive friction. And so the A is going to come in like this, B is going to kind of glance and blow like that, and then go off like that. So that's the problem with this and what you know to be true, right? Well, what you've ever seen is a frictionless pool ball with somebody trying to, drop it in the pocket. You haven't seen that, right? Anyway. Okay, so there's VAY. Could you also do it for B? Here's B. Do you have any impulsive forces on B in the Y direction? No. So you can say impulse of B in the Y direction is 0. That means, that means the momentum before and the momentum after in the Y are the same. Okay, so what's the initial momentum of B in the Y direction? 4/5 times 4. So it'd be mass of B, 4/5 times 4. Is he positive or negative? Positive. So that equals positive. So that equals after mass of B times what is the final velocity in the Y direction? Yeah, it would be V cosine 30. Right? We're going to talk about timing. V cosine 30. Put them all together, you have the right number of equations. Bing, 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 and off you go. Okay. What if you have a truck driving along and you have a tennis ball that comes in and bounces off the windshield? How would you do that problem? Is it impulsive? Yes, it is. What happens to the truck? Nothing. Okay, what are you going to do? How are you going to solve that problem? You can't take the truck and the ball together. So what are you going to do? You're going to take only the ball. Okay, this direction you have impulsive forces. If you just take the ball, in this direction you have impulsive forces. Yes, you do. So you do not use momentum in that direction. What about this way? No, so you apply momentum this way. What do you put this way? Coefficient of restitution. You do coefficient of restitution this way. You do momentum this way. Ball alone. Got it? Good luck. What am I going to do next week? Review. You don't ask questions. It's short class. Yeah, if you want to maximize your number of points, you do 18, but I'm not going to put 18 on.
Is it going to count as extra credit, or is it just going to count as
Look, students are asking for extra credit on homework. You don't. Do it. Because you want to do it. If you don't, it won't be on the exam. I'm not going to put each chapter 18 on this one. What's that? You don't do it. I don't know how to max that. I'll tell you the next one. They're on Blackboard. Hold on to their own answers.
Okay, well.